Bindal, would you introduce or do I do it as you
Ah,
like?
as you say, I don't mind. I mean, it
So
depends
let's
on
do
you.
again half and half. Huh?
Okay, okay.
So we have, since we both are present, we do
Yeah.
it. So are we live? Yes, we are live. So
Yes,
it's a
yes.
pleasure now to reintroduce Dr. Saurav, whose teaching style is now well known to us for the past 2-3 days. After doing his PhD in 2005 entitled Cosmic Phenomena in String-Inspired Spacetimes with Torsion from Jadavpur University, Kolkata, he worked as a postdoctoral fellowship research associate in the Institute of Physics, Bhubaneswar, and then in the University of Lethbridge, Alberta, Canada, followed by Saha Institute of Nuclear Physics, Kolkata, India, before joining as a regular faculty member at the Delhi University. He has taught many core and special theory and lab courses in the curriculum of MSc at DU at DU Department of Physics and Astrophysics, and his main research areas include classical and quantum gravity, cosmology, quantum entanglement, and black holes, astrophysical and cosmological aspects of string. Ma'am,
Yeah,
now
he has more
I,
than 25 research papers and has guided many PhD students so far. His name is included in the reviewer panel of several research journals of international repute and have received recently the Outstanding Reviewer Award 2019 from the Journal of Classical and Quantum Gravity, Institute of Physics, Publishing, Bristol, UK. So welcome, Dr. Saurav. We have the pleasure of your talk once again. And please kindly start sharing your screen.
Mhm.
Yeah, we can see now.
All right. Yeah. So I shall start from where I left yesterday.
Yes.
So I gave the basic introduction of tensor analysis and followed by the definition and categorization of tensors. Uh, uh, and explained the differences between contravariant and covariant vectors, tensors, and so on. So today, and I asked you to go through these notes on the tensor algebra. Um, these are the properties of tensors, um, and there are different kinds of products like the direct product, the contracted product, and the scalar product. And what we define by norm and trace of tensors are given here. So tensors of different ranks, the lengths of those tensors could be found out by taking the scalar product with itself. And the trace means it's a summing over particular set of contracted indices. The sum could be partial as well. So there could be partial tracing as well. Okay, so now we go to the domain of the most fundamental tensors, or what we can say, the building blocks. The first thing that comes is the metric tensor. Uh, Now, recall the foremost criterion in the formulation of relativity theory that the corresponding transformation equations must leave invariant the line element ds squared, that is the squared separation between two infinitesimally close points in space or events in space-time. For example, in Galilean relativity, the corresponding Galilean transformation equations leave invariant the infinitesimal squared separation of points in the three-dimensional Euclidean space. So this is the Euclidean spatial separation, whereas in special relativity, the corresponding Lorentz or Poincare transformation equations leave invariant the infinitesimal squared separation of events in the four-dimensional Minkowski space-time. Okay, so you can see that this guy is actually a quadratic in the coordinate differentials. Okay? It depends on the squares of the coordinate differentials with different coefficients. The coefficients here are all +1, and the coefficients here, this guy has coefficient +1, and all the others have coefficients -1. Okay. In general, the coefficients could be functions of the coordinates as well. Okay. So what we write in general is the infinitesimal distance squared, or the line element written in this fashion. This is, there is a sum over alpha and beta. And here, these cases like the Euclidean or the Minkowskian, here you have only the diagonal terms present. The off diagonals are not present, like cross terms, like you don't have any term which is dx naught dx1 kind of thing. That is not present in this special relativistic metric line element, in this special relativistic line element. But in general, there could be. Okay. And also the coefficients in front, those are in general not constants. So they are actually functions of the coordinates themselves. So in general, it could be written in this way, where you can have all sorts of terms. Like when you break this up, this would be g00 dx0 dx0 plus g01 dx0 dx1 plus so on. Okay. So all possible terms could be there. In these special cases, most of the terms go to 0. Only a few coefficients survive, and those coefficients are of the diagonal terms. That is, when alpha is equal to beta. Okay. But there is a caution. Like in this case here, you only have G alpha alpha term, alpha alpha terms present. That is G11, G naught naught, G11, G22, and G33. Okay, but you can never write something like this for the Minkowski. In special relativity, this way of representing is simply not on. You cannot write repeated dummy indices. You have to write in this fashion. Although you know that only terms with beta equal to alpha would survive. Still, you have to write in this way. You can never write anything in this fashion. A repeated index, like a dummy index, the symbol you are using, you cannot use the same symbol for another dummy index. Okay, keep that in mind. No two indices can be repeated more than once. Okay, you cannot have 3 alphas, 4 alphas, or 3 or 2 or more than 2 dummy indices of the same symbol. If you want to use, if there are 2 dummy indices, then you have to use 2 different symbols. Okay, but you cannot use the same symbol. So this is a word of caution. So in general, G alpha beta could be a function of the coordinates and not necessarily diagonal, as I said. There could be G01, G02, G12, all sorts of terms could be present. Okay. So there could be dx0, 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 dx1, then dx1, 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 dx2, all sorts of terms could be present. In the special relativistic case, only the diagonal terms survive. Okay, and this thing is written here, that the metric, so what is known as this G alpha beta, these coefficients are called the elements of a covariant tensor of rank 2, known as the metric tensor. Okay. This is a metric tensor, or sometimes simply the metric. That the metric G mu indeed transforms as a covariant tensor of rank 2 can be verified, and the verification is given here. Okay. It can be verified straight away. Okay, the first thing is that here lies, yesterday I had explained why special relativity is so named. Okay, because the involved transformations are the Lorentz transformations or the Poincaré transformations. The corresponding Jacobian of transformations are identically one. Jacobians of transformation. So whatever Lorentz transformation you use, the Jacobian of transformation is always one. But ds square is not the Jacobian. I think you are totally listing. ds square is the separation between two events in space-time. Jacobian is the determinant of the transformation matrix. So how can the Jacobian be equal to the ds? So don't have such misconceptions. ds squared is the separation between two events. It's clearly written here. It's the separation, the squared separation between two infinitesimally close points in space or in space-time. Okay, so that is ds squared. That is not the Jacobian of transformation. Jacobian of transformation is the determinant of the transformation matrix from one system to another system. When you go from one system to another, you have a transformation matrix. Okay, and that transformation matrix comes, it was explained yesterday, that transformation matrix comes here. You simply write dx prime as del x prime del x dx. Okay, summed over. So dx prime is del x prime del x dx. Now all these coefficients del x dx, del x prime del x, all those coefficients will form a matrix. Okay, because you have how many equations of this sort? 4 equations, because mu takes 4 values. So there are 4 this type of equations. Okay, 4 equations, and 4 equations you can write them in the matrix form. The matrix that would come out is this matrix dx prime mu del x prime mu del x mu. Okay, so coming back here, in general, this ds square could be written as a general quadratic function of the coordinate differentials, and could have some cross terms as well. And also these coefficients g naught naught, g01, 02, and so on, this g alpha beta, these coefficients, which are called the elements of the metric tensor, are not necessarily constants. They could be functions of all the coordinates. Okay. Special relativity assumes this sort of special type of metric. Okay. And hence it is known as special. because this metric is just taken by hand, by choice, from physical arguments. However, in principle, one has to solve certain equations to get the forms of the coefficients G alpha beta. Each of the G alpha beta coefficients. One has to solve for certain equations to get G alpha beta. Those equations are known as field equations, the corresponding field you take. That field is the gravitational field, because this whole thing is concerned with geometry. So the field you have to consider is the gravitational field. And the field variables are represented by these coefficients G00, G01, and so on. In special relativity, gravitational interaction is ignored. And that's why this special type of metric is chosen. From physical arguments, this special type of metric is chosen. What physical arguments? That was explained yesterday, that when you put ds square equal to 0, you automatically get dx dt equal to c, the speed of propagation of electromagnetic signals. That was the physical argument. Okay. So there lies the difference. This is the special relativistic metric. This is the general relationship which holds in all sorts of relativity, general relativity and further generalized relativity as well. Okay, Einstein's general relativity is not the ultimate one. There are further generalizations, and we are also doing generalizations these days. Generalizations of general relativity. So, but whatever theory you take, this is the quadratic form of the distance separation between two events in space-time. It's just the squared separation between two events in space-time, nothing to do with the Jacobian as such. You take 2 points in the space-time. These points are represented by 4 coordinates, t, x, y, z, and say the other one is t1, x1, y1, z1. Okay, so these are the coordinates. So what would be the distance separation between these 2 points? The distance separation is s squared, and which is equal to c squared t squared minus c squared, sorry, c squared t minus t1 whole square plus minus x minus x1 whole square minus y minus y1 whole square minus z minus z1 whole square. Okay. So this is the squared separation. And ds squared is the differential form of that. Okay. The following are the properties of the metric tensor. First of all, it is symmetric. It is symmetric because we know that the coordinates dx, dy, let's say, these types of products, they commute. Okay, they always commute. So that means when you take the sum, then g alpha beta dx alpha dx beta is same as g beta alpha dx beta dx alpha. So that means g alpha beta is equal to g beta alpha. The next thing that comes is the contracted product of the metric tensor in the contravariant form gives the Kronecker delta, which can be shown to transform as a mixed tensor of rank 2. So the Kronecker delta is in fact a tensor of rank 2. But remember, Kronecker delta in this form, it's a mixed tensor of rank 2. The symmetry property, this symmetry property ensures that there are at most 4 plus 1 over 2 independent components of G alpha beta in a 3 plus 1 dimensional space-time. Accordingly, one can decompose the right-hand side of this equation, in this way. So there'll be G00. We have this set. dS square is G alpha beta dx alpha dx beta. Okay. So alpha and beta both 0. So you have G00 dx0 dx0. Then 0 and beta is a space index, 1 time 1 space. So that would give you 0i. Okay. dx0 dxi, where there is a sum over I. So always repeated indices are summed over. So there are 3 terms: 0, 1 dx0 dx1, 0, 2 dx0 dx2, 0, 3 dx0 dx3. And G0i is same as Gi0. Okay, so you have G01 dx0 dx1 same as G10 dx1 dx0. Since dx0 dx1 is equal to dx1 dx0, you have G01 equal to G10. And hence this 2 factor comes. And finally, you'll have Gij, dxi, dxj. I and j, as I said, these Latin indices correspond to the indices or the labels of the 3-dimensional spatial slice. We have 1 time and 3 space coordinates. The 3 space coordinates are represented by the Latin indices. The full bulk is represented by the Greek indices. Okay, the time is represented by the 0 index. So this is 3-dimensional. So there'll be 3 cross 3. So this Gij would be 3 cross 3. And since there is symmetry, that is the off diagonals from the both sides are identified. So there will be how many? 3. It will be ultimately 3 diagonals plus 3 off diagonals. Okay. If you think this as a 3 by 3 matrix, then if the matrix is symmetric, then there'll be 3 diagonal elements and 3 off diagonal elements. Because the off diagonals from both sides are identified. So there'll be in total 6 elements. So that set of 6 terms. So in all, there'll be 1 here plus 3 here plus 6 here. So that makes it 10. So at most in 4 dimensions, there could be 10 terms involved in ds squared. The property 4.7, that is this property, on the other hand, implies that the norm of the metric tensor is 4 in 4 dimensions. So this is the relationship. So what does that mean? If you trace this, then the trace of the Kronecker delta is delta alpha alpha, which is 1 plus 1 plus 1 plus 1, 4. So, and this is nothing but G alpha beta, G alpha beta. Now, the important usage of the metric tensor is to raise or lower the indices, the contravariant or covariant indices of given tensors. Okay. For example, a tensor of rank 1 or a vector, this is the covariant index. So we consider a covariant vector. The corresponding contravariant vector would be related to this covariant vector by this. So these G alpha betas are used to raise or lower the indices of vectors and tensors in this way. Accordingly, you have the scalar products expressed as A alpha B alpha, which you can write as G alpha beta. So you are lowering the index alpha here by the G alpha beta upstairs. Okay. G alpha beta is the inverse of the metric tensor. And you can write it in this fashion. And since it's a dummy index, you can use any symbol you like. So ultimately, you can write this after summing over. You see, you have summed over. So what remains is A beta, B beta. And since it's a dummy index, you can use the symbol alpha. So what ultimately makes that there is a sum in this, sorry. Sum over upstairs downstairs is the same as the sum over downstairs upstairs. And similarly here. And you may also note that the metric tensor, for the metric tensor itself, you can raise or lower the indices using the metric tensor. So when you do that, then the mixed form of the metric tensor is nothing but the Kronecker delta summed over, that is the trace of the Kronecker delta, which is the norm or length of the metric tensor. So the length of the metric tensor is the same as the trace of the metric tensor. So this is a crucial property of metric tensors. Okay, there are some questions. I can take those questions now. Can somebody prompt me the questions? Chat box. Or I can just carry on here, because these are all abstract things. So at the end, I'll take those questions. Now, spatial relativity alludes to a spatial form of the metric tensor, as I said, that is G alpha beta, often denoted by eta alpha beta, referred to as the Minkowski metric, which is diagonal and with each non-vanishing element normalized to unity in magnitude. So it is diagonal 1, -1, -1, -1. That is, in magnitude, eta alpha beta is delta alpha beta. Explicitly, eta 0, 0 is 1. eta 0 I is 0 for all values of I, and eta ij is minus delta ij. Okay? Because you write the Minkowski metric in this way, ds square as eta alpha beta dx alpha dx beta. So this is eta 0 0 dx 0 square minus eta ij plus dxi dxj, and then twice eta 0 I dx 0 dx I. But you can see that ds squared, the Minkowski metric, is nothing but dx 0 square minus it's like this. So that means the coefficients are +1, -1, -1, -1. All the diagonals would exist. This guy would be 0. Okay. Only the diagonals would exist. The cross terms would be 0. And explicitly, eta 0 0 is +1 and eta 0 I is 0. Eta ij is minus delta ij. So by definition, delta ij is diagonal. Then comes the vectors and tensors in Minkowski spacetime. The components of a vector could be worked out in this way, and you can work out the components in this fashion using these things. In Minkowski spacetime, the raising and lowering of indices would be done using the Minkowski metric tensor. The Minkowski metric tensor has components is. So after raising and lowering, you can have the components of the raised or lowered vector in this fashion. Okay. Similarly, you can have the same thing for a second rank tensor. The second rank tensor can have components or elements 0 0, 0 I 0, and ij. So the corresponding T00 could be related to T upstairs 00 in this way. And in fact, they are same. T0I could be related to T upstairs 0I via this Kronecker delta. And similarly, the others. Now, consider the special case when this tensor itself is the metric tensor, Minkowski metric tensor. So T alpha beta is identified with eta alpha beta. This is the special case. If we consider the case where this T alpha beta itself is the metric tensor, then from these relationships we get the eta upstairs 0 0 equal to 1, eta upstairs 0I equal to 0, and eta upstairs ij is minus the Kronecker delta. So that means the eta alpha beta, the Minkowski metric tensor, and its inverse have the same set of components, that is diagonal +1, -1, -1, -1. For higher rank tensors, you can find the relationships in similar manner. Okay. Let me see. There are many questions in the chat box. take the questions. I've answered ds square is the Jacobian or not. That I have answered. If we can, that is from Durgesh Kumar, if we can transform a metric without coordinate system, then how will it decide basis of those metrics? What do you mean? This is meaningless question. Without coordinate system, we are all concerned about coordinate transformations. How can you do these things without coordinate system? This is meaningless. Then Adumukam, with the condition of singularity, the metric tensor will be 0 or infinity or something new. What do you mean by singularity? I have not talked about singularity anywhere. So singularity is a different issue. The metric blows up somewhere. That is different. Which one is not visible? Can't you see my screen? This is Vauna. Can't you see my screen? Yeah. With the condition of singularity, the metric tensor will become 0 or infinity or something. This is another meaningless question. We have not talked about singularity. Singularity is a different issue that I will not address here, because here we are considering only the Minkowski metric. Singularity means when the metric tensor elements are functions of space or time, and the, say, one of the coefficients g alpha beta, say g00, blows up at some point, at some value of t or x. That is called singular. Okay, but here we are only concerned about the Minkowski metric where the coefficients are constants. So there is no question of any singularity. Okay, as we carry on, the most important topic that comes through is the symmetry and antisymmetry of tensors. The symmetry and antisymmetry is defined only for contravariant and covariant tensors of rank greater than or equal to 2. Symmetry or antisymmetry could either be partial, that is under the exchange of only a given pair of indices, or complete, that is under the exchange of any pair of indices. Then symmetry or antisymmetry of some pattern, partial or complete, of a covariant tensor implies symmetry or antisymmetry of the same pattern of the corresponding contravariant tensor and vice versa. So this means that if we have a symmetric covariant tensor of rank 2, then the corresponding contravariant tensor of rank 2 would also be symmetric. If a covariant tensor of rank 2 is antisymmetric, then the corresponding covariant tensor of rank 2 would also be antisymmetric. Now, here comes an important thing. When we say antisymmetric, what does that mean? Antisymmetric means the what will happen to the diagonal elements of antisymmetric tensors. So you take a, let's say there are elements of some tensors. The off diagonals here is minus the off diagonals here. What will happen to the diagonals? The diagonals should be 0, because you see when you put alpha equal to beta, in that case you have a alpha alpha equal to minus A alpha alpha. Diagonal means you have to put alpha equal to beta. That's what we mean by diagonal. Okay. For example, the metric tensor G alpha beta, it has the diagonal element G alpha alpha, and it has off diagonal elements, that is G alpha beta, where alpha is not equal to. So diagonal elements are the elements which will come here. So for example, if it is a 4 by 4 or 2 by 2, let's say a 2 by 2 or 4 by 4 or 3 by 3, whatever you like, then this is the 0 0 component, this is 1 1, 2 2, 3 3, and so on. So that means here both the indices are same. And when you do that, if there is antisymmetry, then this automatically implies that all the diagonals are same. And the off diagonals are identified. Now, the situation is a bit involved in higher rank tensors. For example, the rank 3 tensor, then there the symmetry could be partial or could be complete. Here you see this has symmetry only in the first two indices. In the first two indices. Here you have symmetry in the last two indices. Here you have symmetry in the first and third indices. But here, if you equate all of them, then you have complete symmetry. You change any pair of indices, the thing will remain the same. So that is called complete antisymmetry. Similarly, you can have partial antisymmetry and complete antisymmetry. See, the complete antisymmetry means if you have some antisymmetric tensor to start with, then all the cyclic terms, cyclic permutations of the indices would be equal, and all the anticyclic permutations of the indices would also be equal. The second thing that comes is, given some tensor, we don't know whether it is symmetric or antisymmetric. A rank 2 tensor is given to you. You can always split that in a symmetric part and an antisymmetric part. Okay. See, you can construct a symmetric tensor out of this tensor, like in this way. This is by construction symmetric. If you interchange beta and alpha, the thing will remain the same. This is by construction symmetry. And here, this is by construction antisymmetry. The symmetric brackets are the ordinary curly brackets. The antisymmetric brackets are this square brackets. Okay. The antisymmetric brackets would be, antisymmetry would be denoted by this square bracket. This is known as antisymmetrization. And this is a bizarre property of only the rank 2 tensors. Higher rank tensors cannot have that. For higher rank tensors, a given tensor cannot be split into a totally symmetrized part and a totally antisymmetrized part. Only rank 2 tensors could be split. Okay. For rank 3 tensors, for example, the total symmetrization means this whole sum. See, you take the permutation, the cyclic permutations of these indices, alpha, beta, gamma, then beta, gamma, alpha. So 1, 2, 3, 2, 3, 1, 3, 1, 2, all of them. And then the anticyclic, that is 2, 1, 3. Then this is 1, 3, 2, and so on. So when you take this full sum, and there are 6 terms, so you have to divide by 6, then what you land up with is a totally symmetric tensor. Totally symmetric means, completely symmetric means, if you interchange any pair of indices, the tensor will remain the same. Similarly, you can construct a totally antisymmetric tensor out of any given tensor of rank 3 in this way. You have to add all those cyclic permutations and subtract all the anticyclic permutations. Then you can verify yourself that this is antisymmetric under any pair of under the interchange of any pair of indices. Okay. These are the ways to work out the components. I'm not going to those details. One important thing is that the trace or the scalar product of a symmetric tensor and an antisymmetric tensor is always 0. This is crucial. The scalar product is by definition this. You take a symmetric tensor S and an antisymmetric tensor A. So S is a symmetric tensor. S alpha beta is minus S beta alpha, and A is antisymmetric. Sorry, S alpha beta is equal to S beta alpha, and A mu nu is minus A nu mu. Then you take the scalar product. Since they are dummy indices, you can use whatever symbol you like. So instead of alpha, you can use beta here. And instead of beta, you can use alpha here. It's your choice, because they will be ultimately summed over. So no matter what symbol you use. But let's say if you interchange the symbols alpha and beta, the thing will remain the same. But A beta alpha, because this is antisymmetric, A beta alpha is minus A alpha beta. So that means S alpha beta, A alpha beta is S alpha beta minus minus S alpha beta, A alpha beta. Okay. So but this led to a problem some years back. Actually, I taught this in the class, and then in a quantum mechanics teacher called me up and said, "What did you take? Tell the students." They are taking the product of a symmetric matrix and an antisymmetric matrix and saying that that is 0. You have to be careful. The product is a scalar product. For example, S alpha beta A mu nu. This is not 0. Only when you take a scalar product out of this, S alpha beta A alpha beta. That means you are summing over the indices. Only then this is 0. So any product, a direct product, for example, of a symmetric tensor or matrix and an antisymmetric tensor or matrix is not 0 in general. But it is the scalar product which is 0. When you construct a scalar out of these two tensors, then it is 0. So these are some definitions. If you're interested, you can go through this. This is denoting the number of independent components of tensors, of symmetric and antisymmetric tensors. I'll not go through these details. Next thing that comes is the is another fundamental tensor. There are only two fundamental tensors from or building blocks. One is the metric tensor. The other one is the Levi-Civita tensor. The Levi-Civita tensor is concerned with the dimensionality, and I urge you to go through these definitions because it's not possible to do all the things right here. There are a plethora of stuff. Um, um, and there is something called tensor duality, which I'll also skip here. But I urge you to go through these details. Next comes the tensor calculus. You can have contravariant and covariant differential operators like this. The components, so the zero component of this operator, this is just del del x. The zero component is del del t or del del ct, and the space component of this is the nabla, which is the space derivative. But the contravariant has del del 0 and minus the nabla. Okay. Similarly, you can have gradients, the covariant gradient, then the contravariant gradient, the covariant divergence, the contravariant divergence, and so on. And finally, you can also write the covariant curl in terms of the Levi-Civita tensor. Levi-Civita tensor is the tensor which is totally antisymmetric. In 4 dimensions, it should have 4 indices. Okay, this is the contravariant version of the Levi-Civita tensor. There is a covariant version of the Levi-Civita tensor as well. The indices could be raised or lowered using the metric tensor. For example, the curl of A, some vector in 3-dimensional Euclidean space, we write that in the index notation as epsilon ijk del jak minus del k. You can simply see this is curl of A. Let's say the first component, that is the x component, curl of A, x component. This you have to write as epsilon 1 jk, then this thing del j ak minus del k aj. Now, the Levi-Civita tensor is completely antisymmetric. What do we mean by complete antisymmetry? Complete antisymmetry means that all these indices should have values which are entirely different. So, if this one index is frozen to a value 1, the other 2 indices must be 2 and 3 or 3 and 2, nothing else. No 2 indices could be same, because then that would be a diagonal, that would correspond to diagonal in that respect, and hence would be 0, since the full tensor is completely antisymmetric. Antisymmetric for the interchange of any pair of indices. So that means you can have only half epsilon 1, 2, 3 del 1, del 2 A3 minus del 3 A2. And Similarly, you can have epsilon 132 del 3a2 minus del 2a3. So this will give you half epsilon 123 is 1. So half del 2a3 minus del 3a2 minus epsilon 132 is minus 1. If 123 is plus 1, then 32 you will get by interchanging 2 and 3. So one pair of index. So hence there will be a minus sign. So we'll have a minus sign here. Then we have del 3a2 minus del 2a3. So this means the half goes. You simply have del 2a3 minus del 3a2, which is del y az minus del z. Okay. This way it's done. Then comes the D'Alembert operator. In a 3+1 dimensional spacetime, there is another useful operator known as the D'Alembert operator, sometimes called the wave operator, which is this scalar product of the operators del alpha, that is del 0 plus del I, and which is in component notation. The tensor integration I will not discuss here. So this ends the discussion on tensors. The details specifically regarding tensor duality I'll do as we proceed to formulate the Maxwell's equations in a covariant form. I'll come back to this tensor duality later on. Okay. For the time being, let's move on to the special relativistic particle dynamics, followed by the covariant formulation of Maxwell's equations. We have to get back to electrodynamics, and the plan is to finish by tomorrow within half an hour at most, and then we have to do certain problems. Okay, so certain involved problems. I'll give you the worksheet latest by tomorrow morning on what problems we have to deal with. Okay. I'll take a break of just 1 minute. Actually, I have forgotten to. I forgot to bring my water bottle, so I'm just going downstairs and bring it. Okay, just give me 1 minute. Okay, I'm back. So let's move on to, these are very abstract stuff, so may not be interesting. So better to move on to other things. And tensor analysis, we are just using as a tool. Tensors are tools to work out what follow next. So it's better not to spend too much time on tensors. Okay. So the next thing, the next topic that comes is the special relativistic dynamics. So the first definition is of the 4 velocity, which is in the covariant formulation, one can construct a 4 vector whose spatial components are proportional to the components of the ordinary 3-dimensional velocity of the particle, and the time component is proportional to the speed c. The contravariant projections of this 4 velocity, sometimes called the world velocity vector, is given by this. This is a 4 vector. This is a Lorentz vector. It is defined in this way. Just as in 3 dimensions, we have the ordinary 3 velocity v. The ith component is given by dxi dt. So v1 is dx1 dt. In a covariant formalism, the dx, one should consider all the 4 elements, that is dx alpha. So there'll be 4 components of this velocity, u0, u1, u2, u3. So alpha can take 4 values, and the time is replaced by the proper time, which is a Lorentz scalar. The proper time is the time recorded by an observer moving with the particle. So it's the time recorded in the moving frame. That is the time recorded by the observer with respect to whom the particle is at rest. So there is a particle which moves with respect to some coordinate system, and let's say a clock is associated, attached to the particle. With respect to the clock, the particle is at rest, and whatever the clock records is the proper time. Whatever the clock attached to the coordinate system records is not the proper time. That is the coordinate time, dt or t. Whereas the proper time is tau, and proper time is a Lorentz invariant quantity. It's given by dt over gamma, where gamma is the constant that appears in the corresponding Lorentz transformation matrix. The details can be found if you have forgotten, or if you want the details, you can look at the chapter 4, which I have skipped. So let me go to the chapter 4. Here, at the end of the chapter 4, you have these notes with you. So look at the end of the chapter 4. There is the section 4.3 where the different types of intervals are defined, and at the end, the proper time and time dilation is explained. So please go through that. The main relation is that the proper time differential is the coordinate time differential divided by gamma. So, this is gamma times dx dt, dx alpha dt, and dx alpha dt has components dx0 dt and dx I dt. dx0 dt is nothing but c, because dx0 is c times t. So dx0 dt is c, and dxi dt, as I said, it's v. Okay. And this is a time-like 4 vector because its norm, you can see the norm here is you can work out the norm like this: u alpha, okay, which is eta alpha beta u alpha u beta. In this way, you can work out the norm. So this will be eta 0 0 u0 u0 plus eta ij ui uj. I'll better use I'm sorry, would be rather better if I use in this way. So this is eta downstairs alpha beta u alpha u beta eta 0 0 u0 u0 eta 0 0 is 1. So this is u0 square, and eta ij is minus delta ij. Now from here, you can see u0 when you put alpha equal to 0. Then you have this component, gamma times c. u0 is gamma c, and ui is gamma times vi. Okay. So putting all these things here, you'll finally land up with this. And gamma square, if you remember, gamma square is 1 minus v square by c square to the power minus 1. So this is c square minus v square over c square to the power minus 1. That is c square divided by c square minus v square. So that will cancel with the c square minus v square here. You'll be left with c square. And this is positive. When the norm is positive, norm is nothing but the length, or the length squared of the 4 vector. Remember, the 4th vector, it's not like the 3 vectors. 4 vectors norm could be positive or negative or 0. If it is positive, then it is like time. Why? Because you remember ts square we have defined as c square dt square minus dx square. Okay, so that means the time is something whose coefficient is positive. So when the norm turns out to be positive, we say that it is time-like. That is, its coefficient, time-like is something which transforms as time. The coefficient is positive. If the coefficient is negative, then it is space-like. And when the coefficient is 0, then it is null. So if u alpha is 0, then it is null. If u alpha is something positive, then it is time-like. If u alpha is negative, then it is space-like. Similarly, you can work out the 4 acceleration, which is the 3 acceleration is dv dt. Okay, here the 4 acceleration will be du d tau, the same way. And as you work out, you will get u alpha is gamma c gamma v. So the derivative will give you gamma dot c and gamma v dot plus gamma dot v, whole thing times gamma. Okay. Here the dot represents, dot means time derivative. And gamma dot can be worked out from this relationship. You can work out the gamma dot. Gamma is this. So you can work out the gamma dot, and gamma dot will come out to be gamma q v dot v dot. So you can write the coefficients in this way, right here. And you can see for yourself, I'll ask you to verify this at home. This is your exercise. I'll put this in the worksheet. This is your exercise. You have to prove this, that the norm of A alpha is negative. That is, A alpha is space-like. And the scalar product of A alpha with U alpha is 0. That can be readily proved. That can be readily proved because A alpha, U alpha is, you don't need to use these expressions. I can tell you. You don't need to require to use these expressions. You just use U alpha, A alpha is d U alpha d tau. And you have, this is dotted with U alpha. So this you can write as half d d tau of U alpha U alpha. And U alpha is constant. So d d tau of that constant is 0. And therefore this is. Okay. So this you can work out simply. But working out this is not that easy. I'll be very happy to see if you try this at home without making allusion to this sort of component structure. You use the definition from the first principle. A alpha is given by this. Okay. So work out A alpha from here, which is, so you have to work out A alpha, which is d U alpha d tau, d U alpha d tau. And show that this comes out to be negative. Negative means negative definite. Then comes the 4 momentum and energy. In a covariant formalism, one can define the 4 momentum of a particle as the product of the particle's rest mass m and its 4 velocity. The spatial components of the 4 momentum correspond to those for the relativistic 3 momentum of the particle, and the temporal component is proportional to the total relativistic energy. So is mass times velocity. So m times the 4 velocity, m is the rest mass. And when you put this in the component structure, then this is gamma mc and gamma mv. This calligraphic m is what is known as the relativistic mass. The small m is the rest mass. And this can also be written as total energy divided by c, and this is the relativistic 3 momentum. This gamma mv is the relativistic 3 momentum. So where this relativistic mass is gamma times m, p is gamma mv, and E is gamma mc squared. Okay, that is the relativistic total energy, rest plus kinetic energy. The interpretations could be found straight away. If you expand this P and E in powers of V over C, and in the non-relativistic limit, you'll find, so you just Taylor expand this, you'll find in the non-relativistic limit, P equal to mv and E equal to mc squared plus half mv squared. Mc squared is the rest energy and half mv squared is the non-relativistic kinetic energy. The second thing is that P and E can be shown to be the only functions of V whose conservations are Lorentz invariant, but I'll not prove that right here. The conservation of P under a Lorentz transformation necessarily implies the conservation of P. And the proof is given here. The proof is given below. Where's the proof? Missed it. No, here. This proof is in this section 4. I'll not go to the details of these things. Another thing you can note is that the norm of the 4 momentum, P alpha, can be written in this fashion, and it gives you E squared over C squared minus P squared. And also you have P alpha, the norm, equal to M squared U alpha, by definition. And U alpha is C squared. So this is M squared C squared. So comparing these two, you get this relationship. If the particle is massless, for example, a photon or a neutrino, then the corresponding relationship is E equal to P times C. So here you can see that you can define the energy even for massless particles. In Newtonian classical mechanics, you cannot define any energy for a massless particle. But in relativistic dynamics, you can. I'll skip these sections. There is one interesting example, that is the Compton effect. I'll not go to those details. If you want, you can look into this. The next thing that comes is the 4 force. 4 force is by definition the rate of change of momentum. Force is by definition the rate of change of momentum. But here it's the rate of change. Rate is with respect to the world time or the proper time. Okay. So this is dp d tau, and d tau is dt over gamma. So this is gamma dp d tau dt, and p is E over C and small p. P alpha was written before. It has components. Yes. Okay. So the time derivative will give you E dot and P dot. P dot is the relativistic force. Remember, this P is gamma mv, not just mv. Okay, and E is gamma mc square. So you can write this in the component form in this way. And by definition, you also have force equal to mass times acceleration. The mass here would be the relativistic mass, which is gamma times m, and the acceleration is a alpha. So you can write it in this way. And this is the relativistic generalization of the Newton's second law of motion in classical mechanics. Now, for a particle moving with instantaneous velocity v, the time derivative of the total energy is equal to the total power dissipated. So this is the total power dissipated. This we all know, that the power is given by F dot v. So as you can see here, F is gamma E dot by C and gamma F. So F is gamma E dot by C and gamma F, and E dot is F dot V. F dot V. So gamma F dot V over C and gamma F. Now, this you can write as F dot gamma V by C and gamma times F. You can write this as 1 over C F dot gamma V and gamma C times F. Now, you have U alpha as gamma C and gamma. So this is the U vector. U vector. Gamma C. This is U0. U vector. U0 is gamma C and U vector is gamma V. So this is nothing but F dot U, and this is U0F. This relation would be crucial when we'll formulate the Maxwell's equations in covariant form shortly. This is the, you see, this is the three-dimensional force, but relativistic. And this is the spatial component of the 4 velocity. This is the time component of the 4 velocity, and this is again the spatial component of the 4 force. Okay. So I'll save this one as well. Then I'll go to the next chapter, which is the covariant Maxwell's equations. All these annotated notes would be given to you. Next is the covariant formulation of electrodynamics. Uh, these are the definitions of the charge density and the current density. Basically, you can see that for a system of charges, n number of charges, charge density is just the sum over those charges at particular locations given by the delta functions. So there is a distribution of charges, and the charges are located at different points, and at each point you have a certain charge Qn. Okay. Since it's a point charge, it can be convoluted. It should be convoluted with some delta function with respect to some origin or coordinate system. And the current density, the corresponding current density is the charge times the velocity. It's, the current density J is rho times V. So this is the mathematical form of that in a more involved way, because the rho will involve this summation. So everything comes under the sum, and you have to write it this way. And we can straight away generalize this to 4 dimensions. This 3-dimensional current density, we can generalize it to 4 dimensions. So this would be a 4-vector J alpha. We simply have, we'll keep this first 2, and we'll just ensure that this X is being replaced by X alpha, since there are 4 components now. Now, you may ask that, well, we are not doing this in a covariant fashion. It can be shown that it is indeed a 4-vector by using this property of the delta function. It's right here. If you want, you can look at this. But what it signifies, most importantly, is that this 4-vector J alpha has components. J0 is C times rho, and Ji is the 3-dimensional current Ji. So that means we have defined a covariant current which encodes both the charge density and the current density. Note this thing. Here, from now on, we'll just refer to this current. We'll not refer to any charge density at all. So that means we'll just need to work with only the current conservation. The charge is already encoded in the 4 current. And then we do the things just similar to magnetostatics. What happens in magnetostatics? Divergence of J is 0. Okay. In magnetostatics, there is no free charge. So in magnetostatics, we have a conserved current only. Divergence of J equal to 0. Here, we are doing the things in a way that there is a conserved 4 current. Conserved 4 current, that is the 4 divergence. 4 divergence is this. Del alpha J alpha equal to C. Okay. So this means that you have del naught J naught plus del I Ji equal to 0. And this simply gives del naught is del naught is 1 over C time derivative c times rho, and del I is this. And so you have the continuity equation coming at once. This is nothing but a conservation equation. This shows the conservation of the forecurrent. So from now on, we'll not make any allusion to charge. In a covariant formulation, there is no, there cannot be anything concerned with charge. The charge is encoded in this forecurrent. So although you can think that this is a machinery which is used with lots of index notations, fine, but it simplifies. It simplifies. You don't need to use this sort of relation where you have two variables, rho and j. You don't need to do that. You only have a variable capital J, a dependent variable capital J, and you have to work with that one. The next thing that comes is that in 3 dimensions, you have the Lorentz force equation, which is this. Now, this can be generalized to a covariant 4 force or 4-dimensional Lorentz force. And as we have just seen, the 4 force is gamma f dot v over c and gamma f. So you just replace the f by fl, this Lorentz force. Okay. Then what you find is that you take the dot product of this with v. So fl dot v. So that will give you q e dot v, and then v dot v cross b is 0. So it will just give you q e dot v. And there is a gamma multiplied, so it will give you q over c e dot gamma v. And the other one is just gamma times fl, gamma times this, which is okay. And gamma v is your u vector, and gamma c is the u naught scalar, and this is your u vector, so you have u cross b. This in the compact form can be expressed by as q over c times the contracted product of a second rank antisymmetric tensor f alpha beta constructed out of the electric and magnetic field three vectors E and B and the 4 velocity vector u beta. So this is a 4 force. What you can see is that in the first you have this u here, and in the second that is the space component, you also have components of u. Let's express this in this fashion, where f alpha beta is some tensor which would be constructed out of E and B vectors. The construction is as follows. F alpha beta is antisymmetric. So all the diagonal elements are 0. F00 is 0. F0i we have to take as the ith component of minus E. And Fij is epsilon ijk bk. So it is written in this fashion. E1 is Ex, E2 is Ey, E3 is Ez, and similarly here. You have to be careful here. This is B downstairs k. B downstairs k is minus B upstairs k, because you have to raise and lower using the Minkowski metric tensor, and the spatial components of the Minkowski metric tensor are -1. Okay. You understand what I mean? That is B1, which is Bx. If you want to write B1, then this is eta 1 B1. That is minus B1. B1 is nothing but the Bx component. And B downstairs one is minus B1, that is the minus Bx component. So while doing this, you have to be careful. Now, the first thing is to, first you have to verify that if you put it this way, so let's say you have F0 L. Then this is Q over C, F alpha is 0. So you're putting alpha equal to 0. So this is 0 beta Q beta. Now this would be Q over C. F beta could be 0 or a space index. But if you put F00, that is 0. So it can only be a space index, F0i Ui. Okay. So this is Q over C. F0i is minus Ei. Ui. But Ui, in the same way, this is nothing but F0i Ui, or you can write this as Q over C U is gamma times phi. So this is gamma dot gamma E dot phi. Okay, or you can simply write it as
Dr. Sur?
yes.
Actually, I have to attend a very important meeting just now. So I wanted to leave with your permission. You please continue till you will continue. Dr. Savita is there. I will just leave to join the other meeting. I hope you don't mind.
Okay, okay, no issues. Yeah.
It
issues.
cannot be postponed. The meeting is on. So
no, it's okay. Okay.
You.
Yeah, you carry on. No problem.
Yeah, please. Thank you. Thank you.
Okay, so this is minus EIUI. Now you have to check. Minus EIUI is E dot U plus E dot U. Why? Because let's do it here. You see, EIUI, that is eta ij EIUJ. And eta ij is minus delta ij. EIUJ. And this means that EIUI is minus E dot U. So from there, this minus sign is taken care of. It comes E dot U. So the first component is E dot U. Similarly, you verify that the other component, when you put from in this relationship, when you put alpha as a space index, okay, put Fi L, then this would be Q over C Fi beta U beta. Now there could be Fi0 U0 plus Fij Uj. Two terms could be there. And those two terms will give you this. When you'll use these relationships, please do try at home. So this is the covariant formulation of the Lorentz force equation. And here it is shown that this is this shows that the tensor F alpha beta is this object F alpha beta is indeed a tensor of rank 2 because it transforms like a contravariant tensor of rank 2. This tensor is known as the electromagnetic field tensor. This tensor F alpha beta, this is the electromagnetic field tensor. And this is the most crucial object. We are going to write the Maxwell's equations in a 4-dimensional language with the electric and magnetic fields replaced by the electromagnetic field or electromagnetic field tensor, and the charges and currents, the sources, replaced by the 4 current, which is here, J alpha. So that is the task. Now these are the ordinary Maxwell's equations. You have the Maxwell's equations, these 4 equations. In index notation, divergence of E is 4 pi rho. Divergence of E, rho is J0 over C. Remember, J0 is C times rho. So rho is J0 over C. So that's what we have put here. And divergence of E is del I E I. Okay. Now you can ask, why is there no minus sign? Because when I write something like A dot E, then this is minus AIEI. But divergence of E, I write plus del IEI. The reason is simple. Let's get back to this. You see, you have to go through these details, especially in the tensor calculus. The covariant derivative, the 0 component, is del 0 and this nabla. The contravariant one is del 0 and minus nabla. Okay. Whereas if you consider a vector, a contravariant vector, A alpha, that has components A0 and A, whereas A alpha has component structure A0 and minus A. Okay. So see the difference. This has been done before. This has been done, it was shown. A alpha is A0A, and A alpha is A0 minus A downstairs. But when you take del alpha, then del alpha is del 0 minus nabla, and del downstairs alpha is del 0 plus nabla. Why? Because because del 0 is del x. Del alpha is del x alpha, and x alpha is a vector. So the vector comes in the denominator, and that's why you have this thing. Okay. So that is one thing. And similarly, the other equations could be written. You have to be careful with using the Levi-Civiters. It could be written like that. And from there, you can see that the first two equations, these two equations, the equations which are inhomogeneous, the right-hand sides are not zero. They're inhomogeneous equations. They can be clubbed together in this covariant equation. EI is Fi0. EI is Fi0. So you put EI equal to Fi0. Put EI equal to Fi0. So this equation, you have del I Fi0, then 4 pi over C J0, you can write. And similarly, you have to write the B and E in terms of the components of the F tensor in this way. Then you can see at once that these two equations, 3.3, these two equations, they form the components of del alpha F alpha beta equal to 4 pi over C J beta. You see, the free index is beta. So you have one component is from this equation. One component is del alpha F alpha 0 is 4 pi over C J0. And the other component is del alpha F alpha I is 4 pi over C Ji. Okay. And from there, you have these two relationships. So this thing implies that this alpha cannot be 0 because F00 is 0. So you have del I Fi0 equal to 4 pi over C J0. And from here, you have del J, I should use something else, K of Fki plus del 0 F0I, because here alpha could be 0 or could be a space index. There is a complete sum over alpha. So first I'm summing 0, 0, then kk equal to 4 pi over C Ji. Now compare this with these two. So these two are component equations of this equation, this covariant equation. Okay, these two are component equations of this covariant equation. This is known as the covariant Maxwell equation. I'll start, I'll resume from here. What will happen to the other two equations, that I'll come later. And then the covariant formulation of Maxwell's equations should be completed, and followed by the transformation of electromagnetic fields. And we'll do problems on the transformation of electromagnetic fields. Okay. So tomorrow's the last two lectures are devoted to that. I'll send you the annotated files latest by tomorrow early morning, and also the worksheet for tomorrow's classes. We'll do some problems tomorrow. I'll end here. If there are any questions, I'll be happy to take.
So students, if you have any questions, you can ask them now.
I think we should give them time to think over asking something. So if time permits, we can have a 15 minutes question answer session tomorrow at the end of these lectures and illustrations. They can
sir.
think of questions also. They can frame the questions properly and ask.
Okay, sir. Thank you so much for such a wonderful and informative lecture. I hope students have enjoyed a lot.
Yeah, you are welcome. Shall I stop this sharing?
Yes, sir. Yes, sir.
Okay. I'll send this.
Sure, sir.
Okay. I'll send this this annotated notes by tomorrow morning, latest by tomorrow morning. I'll try and do tonight, but if not possible, then tomorrow morning I'll send this.
Okay, sir. Thank you so much. So students, here we are end for the today's both the set of sessions. So tomorrow we have me with you all for the solid state physics numericals, as you asked about them. And the second lecture would be by again Dr. Saurav Soor sir. So see you all tomorrow, and have a good night. Okay, thank you so much, sir. I will formally end the meeting over here. I'll stop the recording and then I'll stop the live streaming.